Welcome everyone. Hope you can see and hear me all right. And well, I definitely see that you can't see me properly because I'm using the wrong camera. Sorry, let me quickly fix that. Okay, much better now. Sorry for technical glitches. I did some changes to my stuff. Welcome to Iron Beetle, the show where we look at the Target Beetle's source code, trying to understand how to build a distributed database for financial accounting, which is super fast, super reliable, written in Z, doesn't allocate any memory at runtime, and in general is cool in a bunch of different ways. So let's dive straight in and start from the recap of the past few episodes. These few weeks, we've been looking at the storage layer of Target. What data is stored by the database on the hard drive, and how exactly does the data get from random access memory to disk and back from disk to random access memory. In particular, we've been looking at the LSM tree, which provides a persistent, as in on the hard drive, sorted array of items, and we looked at the grid. The grid is the underlying building block. Basically, the idea of the grid is that you slice your data block into data file. You slice your data file into blocks of half a megabyte each, and then you do all input-output in terms of these fixed size blocks. And we've looked at how grid does reads and writes. One important mystery there was that although Target Beetle assumes that the disk can fail and that it can return garbage data or return error or whatever, the actual low-level storage API in Target Beetle kind of doesn't return an error. You read something from the grid and then you get back your data and there isn't any kind of an error in the signature. And the solution to that mystery is that Target Beetle implements transparent repair. So when trying to read a data block from grid, Taggable knows block address and blocks checksum. And if for some reason the block isn't found or is corrupted on its local disk, a replica just goes and transparently asks other replicas to send the block with this data to replica. And oh dear, looks like I am for some reason disconnected from Twitch, so let me try to reconnect. Okay, I should be back online, but don't worry if you missed anything. That was just a recap of last episodes, and what's more, all of the episodes are recorded and uploaded to YouTube, so if I'm having some technical troubles with Twitch, which I do pretty regularly, well, then you can watch the recording on YouTube, and if you have any questions, then please feel free to ask them in YouTube comments or in the during the next episode. Okay. Where we were. Yeah, we were talking about how if a replica fails to read a block of data from its local disk, it just transparently repairs this block from other replicas. And this isn't reflected in the underlying API. The underlying API just gets a block, and it doesn't care whether this block was from its local disk or from some remote replica. Okay, so that was a long-winded recap of the past few episodes. What are we going to look at today? Well, today we are going to look at block cache. How Taggable avoids reading data from disk every time by transparently caching blocks in memory. So let's dive right into the source code. And let me check if I'm still online on Twitch. Okay, well, it seems fine. Hopefully I won't be dropping anymore. Okay, so grid and grid cache. This is that structure which is going to hold blocks in memory to avoid hitting the disk. Before we discuss how this cache is implemented, it's important to discuss on the high level why do we even use this cache? Why not page cache? So, if you recall, modern operating systems, modern CPUs support so-called virtual memory, where your address space is subdivided into pages, and there is a mapping between pages and physical RAM. And because there is this extra layer of mapping, because there is this extra layer of indirection, operating system can play various cute tricks with this. And in particular, one way that Linux, for example, uses this virtual memory subsystem is for transparently caching disk data. So in general, there is no free memory if you run Linux, because every memory which is not used by any of your applications, Linux transparently uses for disk cache. So if there is some spare pages and you read a file from disk, what Linux is going to do is that it's going to read the actual data into some of quote free pages, and then use that data to speed up disk access. And in general, before we go to general, the cool thing there is that this happens completely transparently in the API. So you have your standard read syscall, which takes like file descriptor, and then it takes offset, and then it takes buffer, like where to read, and returns number of bytes read or error. And like this doesn't say that, hey, there is caching, or hey, there is no caching. But actually, most of the time there is this caching, which is using page cache. And that's actually really smart for majority of the cases where you access the disk. Why? Because this is an operating system level cache. And that means that it is shared across all applications. And additionally, it is dynamically sized, meaning that if there is spare RAM, you have more cache space. If you launch more applications, if you open more browser tabs, well, then the amount of like quote spare RAM goes down, and the cache downsizes, but then you can use more applications. This is really something that only operating system can provide, because only operating system has an entire view of what are the applications, what reads and writes they are doing, etc., etc. So that's why kind of, yeah, in general, you should not try to cache on disk data. You should leave the operating system do this in a smart way, because that would be probably better than you would do it yourself, and also it would have this extra nice property that it's going to be shared across all applications. There is like big problem with this whole infrastructure when you get to write in databases, because in the databases you want to guarantee data durability, and in particular if you do write syscall, that's for completeness write a prototype of write, which is again the same essentially. If you do a write syscall, you want to be sure that your write actually hit the disk and that the data is actually recorded, because, well, all various consensus algorithms, all various recovery procedures generally assume that, hey, once you acknowledge something, the data is written. To kind of to give a very specific example, to not indulge into excessive hand waving, let's open our message header and let's look at the prepare OK. So if you recall our consensus lectures, prepare OK is a message that replica sends once it acknowledges that it has received a particular prepare, a particular bunch of transactions, particular batch of transactions. And like the guarantee that is provided by prepare OK message is essentially that this replica is going to be able to provide this prepare, particular checksum prepare, yeah, this prepare with specific checksum, no matter what. If it is like a killer to start it will have this prepare, unless, of course, disk completely crashes. And well, if target middle you're using cache, and if we did a write and the write hit the cache, and we responded with prepare OK, but then our machine crashed and the cache began busted because, well, it is in a random access memory, in volatile memory, then that would be incorrect. So kind of like replica said, hey, I guarantee this prepare, but then actually it crashes, restarts, and there is no prepare nowhere. Well, kind of like there is a syscall which allegedly helps with this thing. This syscall is called Fsync. So the idea here is the application, my database, data file, let's actually do some strong typing here. Let's say that this is actually file descriptor. Yeah, so the idea is that you write a bunch of data, like at some offset, and at this point, yeah, you don't know if like hello world actually hit the disk. It might still be in operating system's memory. So then you do fsync, and after fsync returns, well, you know your data is there. And this kind of like, if you don't look too closely, looks reasonable. But if you take a closer look, there's actually a bunch of problems with this approach. Well, the first one is like, like there is error handling. Like we like try this read, try that read, and then write, and then we try fsync. And any call can fail, but understand that writes normally don't actually touch the disk. They only copy data to some kernel memory to quote free pages. And that means that like these two tries don't actually report IO errors. Only this one does. So the first kind of like problem on like just like the API design is that fsync, when it fails, it doesn't tell you which write failed. So like if fsync was successful, if you don't have any kind of like disk errors, then well, you know that everything's fine. All your data is like hopefully on disk. But if it does fail, well, you know that something went wrong, but you don't know what was that exactly. So that's kind of like one problem with fsync. It gets worse. So what do you do when fsync returns an error? And what operating system does that fsync returns an error? Well, some operating systems, some file systems just clear this faulty flag. So if you like return fsync and like it fails, so you say, okay, let me like catch this error, and then fsync again, and this one might succeed without actually writing data to the disk. So kind of fsync kind of doesn't really like guarantee you that the data is there if there is one error. And well, you kind of like can say, okay, well, fine. If fsync if fsync returns error, I'm just going to safely crash, just like panic, so that I know that hey, there is no like this problem that hey, if I call fsync twice, the second time it doesn't return error. But well, what happens like like the second problem here is like fsync operates on file descriptor, and well, it's actually like not true. It operates on the real file on like the specific set of pages that correspond to this file. So what might happen is that this happens in a different process. So a different process crashes. And then your process, when it does fsync, doesn't get an error because the error bit is faulty, is cleared after fsync. And then you kind of like assume that your data is safe, but actually, well, there was some intervening process which caused interference. And this is kind of like This particular issue is the consequences of an API, because Fsync doesn't tell you which writes succeeded and which writes failed. It tries to guarantee you that all the writes up to the given moment in time, but that is an implicit shared global state, which, as usual, causes all kinds of problems. But it gets even worse than that. Okay, suppose there is no. Suppose there is no separate process inside, and you do Fsync. Fsync returns error. You crashes. Okay, everything's fine. You restart, and well, so here we restart. Probably once you restart, you're going to read your data file to understand what is written there. So you go and read your data file. Let's say that we have some buffer. So we read. And you know what might be happening here? Well, this hello world is still in page cache. It is still cached by the operating system. So when we read it from the data file, we are actually reading it from disk. We're reading it from a page cache. And after restart, we see the data file as if it contains this data. So here we might assume that the data are durably persisted, while actually they aren't. Because, well, if at this point, not our process, but the entire machine crashes and restarts, then it won't have this data on disk because it was only in memory. So kind of like the TLDR is that Fsync is kind of advisory API. It might be a good idea to call Fsync to, if you use page cache, it might be a good idea to call Fsync to maximize the chances that the data are safely stored, but it doesn't really provide you with any kind of guarantees that you can rely on. There is because there is this global mutable state of pending writes. You cannot really understand whether writes are on disk or not, because if the writes were, if Fsync was done by a different process, for example by your own database before the current restart, then you cannot get back to those errors, and those errors might actually affect your current view of the world. So that is the reason why Target opts out of page cache. We don't use page cache. We use so-called direct I/O. We ask operating system, hey, please don't cache our reads, don't cache our writes. Let the data go straight to and from the disk. We'll handle the caching ourselves, and we'll handle error handling ourselves. The benefit there is, because there is no cache, we know that any hardware error, we are going to immediately observe, and it won't be masked by the operating system. The flip side, of course, is that now we also opt out of this smart operating system capability of sharing the disk cache between multiple applications. So, for example, if a different application at the same time will be reading Tiger-Brittle's data file, it would have to use more memory because it won't be able to access the cache which is private to our database. But in general, Tiger-Brittle is designed to be more or less the single important process on your particular machine. So we kind of intentionally try to monopolize all the resources, and we don't try to implement, this extra flexibility, like the lazy memory allocation that Linux does. We kind of say, hey, Tiger-Brittle needs this amount of RAM, this amount of CPU, and if you give it the resources, it will always function, it will never fail. Which might lead to less efficient resource utilization if you mix target with some other processes, but we don't care about that more than we care about the system actually being reliable and providing guarantees. Okay, so that was much done. Let's look how this actually implemented in the code, and let's go up to the actual IO code and see how we open the data file. Okay, so how do we enable direct IO? This is open file function. We take a directory, we take a path inside this directory, and the first thing we do is that we set up the set of flags. Like obviously we want to read and write data file. We also set the desync flag, which is essentially Fsync on every write. We explicitly ask operating system that, hey, please, never ever try to cache this stuff. Always put things directly on disk, and always read things directly from disk. And as a sanity check, we pass visual clock exec flag, so that if for some reason we decide to fork our process, although we don't do fork, but well, maybe just in case as a sanity check, that the file descriptor is not inherited, because for target it's pretty important that no one else tries to mess up with the data file. Okay, so what do we do next? Okay, yeah, so we can open file, we can open existing file, we can create a file. We want to distinguish these two cases in the API to minimize the chance of operator error when they think they, create a new database, but actually they use the old database. So we do some sanity check here. Then yes. Then additionally, here we add this direct IO flag to the set of flags that we request, because we do want to we do want the writes to hit the disk. Why we do this conditionally? Why not always require direct IO? Well, the thing is, not every file system supports direct IO. So for example, if your file system is a TMPFS, so just a memory file system, we obviously cannot just directly write to disk because there is no disk. Another fun case is if your disk is fully encrypted. If your disk is fully encrypted, the operating system cannot directly write to it. It needs to apply its own encryption before data actually hits the disk. But we still, especially for development, we do want to be able to run on TMPFS. So it's only for production use cases that we really require direct IO. So that's why in production we panic if there is no direct IO, but otherwise we just give a warning and let you run your tests. Then, yes, then we open the file. We lock it, and this is a fun thing I really wanted to show this. So recall in the discussion about Fsync, I said, well, what happens if you Fsync, you get an error, you crash, you restart, and then you read the data from cache. So as a defense in depth against this, after we have opened the file, we Fsync before we do any writes. Because, what if some malicious process or maybe some just misconfigured process try to write to the data file? Well, we want to see those writes hit the disk so that we have a consistent image of what's actually on disk. And that's why we, do Fsync before we even try to do anything with this file. And yeah, I guess those are just some extra checks. So yeah, that was kind of like, not a lot of code, but a lot of talking about that, hey, we do really want to use direct writes because direct I/O, only direct I/O allows us to carefully control for errors on disk, and this is how you actually do direct writes. The fun thing is that, the API is exactly the same. The read and write syscalls retain their signatures that you don't need to adjust application. You don't necessarily need to adjust application code further up the stack. The only thing changes is the guarantee, because usually write syscall guarantees that the data is only in operating system's page cache, but with IO Direct and Fsync, you get a guarantee that the disk acknowledged write. Okay, there is an excellent question in Twitch chat, and the question is about security, like security of IO Uring in particular. So IO Uring in general is quote unquote, quote, insecure in the sense that, there are some security related bugs. And IO Uring is disabled on Google's servers, I believe, on most machines. It is disabled on Android, etc., etc. And the question is, if IO Uring is insecure, then why Target is using it? Is it safe to use IO Uring in the context of Target? And the answer here is that yes, in the context of Target, our specific usage of IO Uring is safe because, as far as I understand, those vulnerabilities are of a very specific kind. Those are sandbox escape vulnerabilities. So Linux in recent years to support containerization, virtualization, got a lot of APIs for locking down processes, for building sandboxes. So for example, you could use namespaces and C groups to say, hey, this process can only see like this particular corner of a file system, and there is no way for this process to access anything else, even if the process manages to get access to the root. And the way this is implemented, I haven't looked at it, but I suppose that there is a bunch of checks in the kernel where, like, for example, the application does like an open syscall for a file descriptor, the kernel allegedly looks at the file descriptor, looks at the path, and figures out, should this process be able to read the data? And if it is not, then the access is denied. And for IO Uring, those checks are not entirely complete. So it might be the case that, let's say you do a discrete using normal broken resource call, and you get denied by some security mechanism inside the kernel. And then you open IO Uring, and then you try to do the same read from within IO Uring, and that actually succeeds because, IO Uring doesn't have as time-proved track record of enforcing sandboxing guarantees of Linux. Why this is bad? This is bad because using IO Uring, you can escape the sandbox. So imagine that your Android phone runs a sandbox process, and that sandbox process has access to IO Uring. And now assume additionally that there is a vulnerability in that sandbox process which allows for remote code execution. Normally that is not a problem because, the process itself is sandboxed. And when we get RCE in this process, the attacker, cannot escape the sandbox because, there's a sandbox. But if the process actually can access IO Uring, then what this compromised process can do is that, it can create IO Uring and then do syscalls through IO Uring, escaping the sandbox through vulnerabilities in IO ring, and that would be bad. So hopefully this explains the picture, like the problematic picture about IO ring. So it's not that. So important thing here is that the process, the compromise process, doesn't even have to use IO ring. It only needs to have access to the syscalls. Because we assume that, well, the attacker gets a remote code execution there and can craft arbitrary syscalls using IO ring. And that's why, yeah, if you do sandbox and you generally want to lock down access to IO ring, because it is not as secure as of now. Like I'm sure that, well, with time, all those bugs will be fixed and this interface will be secure, but well, it's not the case right now. Now, why this isn't necessarily a problem for Tagemitl? Tagemitl already assumes that all the processes it communicates with are trusted. So Tagemitl is not directly exposed to the internet. It is exposed to API gateways, and those API gateways are assumed to be trusted. So there is no need to sandbox the Tagemitl process itself. And then kind of like, well, our specific use of IO ring should be pretty safe, because, well, we don't use any kind of like fancy syscalls with fancy flag, which attacker would have crafted. We use just, well, actually, let's see this read. Yeah, like that's like, you know, this is the entire of our IO ring interface we use, and I don't think it's actually possible to somehow break Linux using only those syscalls. The other question is that, of course, if Tagemitl is running a sandbox and then someone's getting a remote code execution for Tagemitl, and then, well, then they could use sandbox escape, can use IO ring to escape the sandbox, but, well, you generally shouldn't be running Tagemitl in a sandbox because you assume that everything's trusted. One thing I want to know as well, why are we so sure that you cannot, well, just remote code execution Tagemitl? And the answer here is, well, we are not using Rust, we use Zig, so we don't have, you know, type system guarantee that we don't have undefined behavior and whatnot, but we do static memory allocation, which by construction removes most of our memory errors. We do pervasive fuzzing, and we use a very simple code with very simple data structure. So we don't have any kind of like JSON parsing or protocol parsing. We don't do parsing at all. Like all our data structure are just like fixed size buffers. And in general, we account for every specific byte in our data structure. So while there is like no mathematical proof that there is no remote code execution in Tagemitl, I think that that is like generally extremely unlikely. And of course, if there is NRC, that would undermine like all kinds of guarantees that we actually provide. TLDR. The danger of IO ring is that it allows for sandbox escape types of vulnerabilities. So you shouldn't be running Tagemitl inside a sandbox as a part of some untrusted code base. But if you do assume trust, then, well, it's fine. Okay. Let's move on, I guess. Finally. By the way, that was a very great question. Thanks for asking. I actually should have proactively covered that at some point. Okay, the next question. Could Tagabidal use IO-ring for network stack? Yes, not only could we actually use for we used for network stack. There is like read, write, send, receive. So yeah, that's. I think that was even like the first or the second lecture, because this is like message bus is our network interface essentially, and well, it goes through IO-ring. And again, the important thing is that we don't do HTTP, we don't do TLS, we do super simple protocol of just sending fixed size data structures over TCP. So this requires us to assume that our networking peer is a trusted process, but it massively reduces the amount of like tricky code you need to write to deal with networking protocols. Okay, so we don't have much time left, and I'm thinking whether we should try to cover set associative cache or whether it is best to leave it to the next episode. Well, let's do it. If you think you can, if you think you can't, you're both right. Okay. Set associative cache. Well, how does set associative cache? Well, set associative cache is the. Well, actually, I know what we do. We'll look at the interface of the cache and how it is used by the grid, and how exactly it is implemented internally. We'll learn next week. Okay, so let's see. This is set associative cache. It's interesting. So we are going to cache block addresses. So you see that set associative cache, as usual map data structure, is parameterized by the key and value. And as usual for data structures in Tagabidal, key is a subset of value. So kind of like, we say that like key is just part of value. There is no like a pair actually. And for our usage of set associative cache in the grid, the key is just the address of a block, U64. So this key from value function, this function which extracts key from value, is just identity. It just returns address as is. Okay, so let's look how it is, because I think what would happen here is that a set associative cache will, well, internally it stores things in an array. It's slightly jumping in the implementation, but well, you see, it's just internal, it's just a single array as a general kind of thing. Systems programming is very easy, everything's just arrays. So rather than using this cache to extract value, we'll be extracting just the index from this array. And we'll use the same index for these cache blocks. Okay, let's look at the usage of a cache. First, initialization, which is relatively easy. So we pass the allocator to actually allocate memory, and we pass the number of blocks we want to cache. And I want to trace this to the command line argument. Read open. Read. Okay, so when we initialize the grid, we also pass this grid cache block counts, and this is passed as an option to replica. So in the main, when we do replica init, oh, now we do replica open. Well, where do we create a replica? Yes. Oh, right, it's instance of the replica open. We pass these grid cache blocks, and that comes from our command line arguments. And that is, yeah, and that is just a CLI argument. So this thing here essentially goes straight through whatever user passed on the command line, and it defines the size of the cache. Okay, let's look at the usage of the cache. Okay, so this is what I've been talking about. This is write callback. So we have written a block to disk, and now we can safely put it into our cache. Okay, so we call this upsert method. Upsert is a portmanteau of update and insert. So that means that insert or update. We don't know whether the value is the key. And what it returns is that it returns the... actually, let's just see what it returns. It returns the index, whether it was updated or inserted, and the evicted value. So for us, okay, why aren't we looking at the evicted value here? I guess this doesn't really matter, because, well, if we have inserted okay, yeah. Last time I was like super fuzzy with this particular 3 lines of code, and I'm still super fuzzy here. So okay, let's try to get it. Okay, we inserted the address of a block. We got the index. So now we say that, okay, whatever address before was in the cache, now this index should hold the block of this address, and we put our block right into the cache. Okay, and the writer gets back the block that was previously there. Okay. Okay, so I think what is like the mystery about the handling of evicted block is going to be evident on the read path. So presumably what we do on the read is that we ask the cache, hey cache, here is a block address. Please tell me the index where this block should be at if it is cached. And the cache will get us index. Then we'll go at that index and see if the block is the one we are looking for. And if it is, well, we won. And if it isn't, well, we need to go to do and go the right. So in other words, we don't explicitly evict the old block from the cache. Just overwrite it. And instead, on read, we are going to check if the block is what we want. So, okay, let's, or even, or I think we won't even have to check that the block is, yeah, I don't think we even have to do extra check, because, well, our cache stores addresses inside. It's essentially a hash set of addresses. And if we ask the cache about the address, and it is in the cache, then that means that the actual block at the corresponding index is the block with that address and not some other block. So yeah, we don't need to explicitly evict anything. We just give this existing block that was previously in the cache at that position to the caller to use instead. And this is the last thing was super confusing, so we'll come back to this a little bit later. But now, just to double check our theory, let's look at the read path. Okay, yeah. Okay, yeah, read block from cache works exactly as we wanted to. So we ask a cache, hey cache, here is an address. Do you have this cached? And if you do have this cached, then what's the index? Well, if we don't get the index, we say, hey, we failed to read the block from cache. If we did get back the index, then we return the block. Interesting. So we still need to compare blocks checksum because blocks are actually mutable. Well, it might be the case that at one point there is one data at a particular block on disk, but at a different point in time, well, the data gets overwritten. And sometimes we are sure that the data is what it should be, but sometimes it's actually not the case. So we do need to double check that the checksum corresponds to others, and that's again another important big invariant that we always use a checksum and an address together as a pair. Okay, so I want to okay, yeah. I wanted to explain this thing about swapping blocks. So let's look at some code which uses grid, which is, well, for example, some tree. I think the tree should use grid. Grid. Well, right block. Who does right block? Okay, so presumably, well, create block, because we do distinguish at the API layer whether we are creating a new block or whether we repairing a block with create block. Well, we haven't looked at neither compaction or manifest log, so this is going to be slightly confusing, but never mind. Okay, so when we write a block, we pass a pointer to a pointer to the data. So, for example, like this thing stores a table builder, and it would contain blocks. So builder points to some memory, some chunk of memory. This chunk of memory is filled, and then we ask grid, hey grid, please write this memory. what grid does is that, well, it wants, obviously it wants to write it to disk, but it also wants to put it in the cache because there is temporal locality. If we have just written this data, it's highly likely that we are going to read this data back quite soon. So the grid also wants to cache this data. And the way this works is that, well, there is this data already in memory. This is the data that Table Builder accumulated in essentially this block. So what grid does is that it essentially steals this block from the builder and puts it straight to the cache. But well, it kind of like cannot just steal the block. It needs to give something back. Otherwise, we will have to do this block allocation deallocation dance with dynamic resources, and that's exactly what we avoid. So the contract of create block is that you pass it a block, and the grid steals the block from you and puts it in the cache. And instead, it gives you back a blank block to use for your next write operation. So that's why in the grids that's why in the grid when we stole colors block and substituted some different block in place, we zero out the header of the block to make sure they don't accidentally use wrong data. Again, so kind of a cute thing. Like pedantically, you might want to actually mem0 the entire block, but that would be what would be pretty slow. So we just zero out the header here, and because we pervasively check checksums and whatever everywhere, just zeroing out the header should be enough to catch any misuse. So kind of like our code is probably correct. So we could just comment this out because, well, we every code would assume that the block is blank and needs to be overwritten. But as a defense in depth, we actually go and overwrite the header, which is going to break anything that tries to misuse this. Okay, so that was one loose end which I want to cover, like that we can like swap blocks. Another thing, when I was discussing Fsync and desync and how we do direct I/O, one thing I didn't cover is that, well, what do we do if the write actually fails? So for reads, if you recall, what we do is that we just pretend that no error happened and just set the entire buffer to 0 and let the caller to check the checksum and do any correction using data from other replicas if they need to. But for writes, obviously, we kind of like cannot do this because, again, at the consensus layer, if we reply with prepare OK, we guarantee that the data is on disk. And if we get an error that the data is not on disk and we need to do something wrong, let's find out. So let's look at how this is done. This is probably storage write. Okay, yeah. And also kind of like, what are really nice is that you see kind of like this grid is like pretty large data structure. Like there's a lot of happening here. But there is only a single call to storage write. So this is what you want to see in the greatly architectured code. You generally want to have very few call sites for various things. So kind of like rather than a particular module going through like long-winded paths and going to a layer down through many multiple ways, you actually want each module to look as a funnel where it takes some input, it like processes it, it like arranges it, and then there is only a single place where it goes to the layer deeper and actually does. And that's what we see here in the grid. There is only a single call to underline storage. And let's go to storage and see how this is actually implemented. So again, this is not a simple atomic operation because we want to write entire buffer of data, and that might require several syscalls. So this is essentially a loop, a synchronous loop. So we go and start a write, and after write is complete, we handle error. And if this is an input-output error, we panic. And input-output errors are actually pretty funny. So generally, probably the disk is going to be SSD. And the thing about SSDs is that they have, I have a very cute little birdie right outside of my window, sorry. Okay, sorry birdie, I have a Twitch right now, can't look at you. Okay, so I'm lost, yeah. SSDs internally also have like blocks, and they have error correction in a sense that over lifetime of the SSD, when you read and write specific, I don't remember how they're called on SSD, like blocks, cells. If you write specific cells multiple times, the cell might die, probabilistically. It might or might not die. So inside it has like hardware to reassign broken cells. And like so for example, when the disk tries to actually fulfill your write, it like writes something and then it realizes, hey, actually the cell I'm trying to write this to is dead, so let me pick a different cell. And that's why if you see a hardware write error from the SSD, it probably means that like the disk is completely dead and no other write will ever succeed, which is different from spinning disk, because well, in spinning disk I think like if some rotating thingy, some rotating disk is broken, well maybe another disk will be correct. Okay, but if this is a different error, we also conservatively panic. And finally, if we return 0, just in case, we also return, we also panic. So that's kind of like, yeah, that's the error handling for writes. If our write fails, what we do is that we just crash the entire process and restart and don't respond to our promises. So, okay, I guess that kind of like concludes today's episode. It was a little bit all over the place, so we covered a bunch of things. We covered the so-called Fsync gate, why it's impossible to use Fsync correctly in a database which actually guarantees durability. We covered direct I/O and how we actually open files safely. We talked a little bit about security implications of IOU ring, how IOU ring is vulnerable to sandbox escapes, but if you don't have a sandbox, that doesn't really a problem for you. And finally, we looked at the cache in the grid, like all this, like the API of the cache. The fact that, well, somehow grid caches blocks. Internally, the cache is essentially an array of block addresses. And when you operate with the cache, you only look at the indexes. So you give address to the cache and it returns you the index where this address is stored in the cache's internal array. And finally, we looked at this cute trick that you want to cache writes, But when you cache writes, you probably want to put the in-memory data which was allocated by the caller right to the cache, because, well, why not? You already have this in memory, you don't want to meme copy this into some separate block in the cache. But that means that you actually need to steal this block from the caller and substitute it with something else. Okay, I guess that's it for today, and see you next week at 5 p.m. UTC on Twitch. And if for some reason you cannot watch Twitch, or if as usual I'm having some technical troubles, then feel free to watch the episode in recording on YouTube and ask your comments there. I in general try to read even YouTube comments and answer either on YouTube or maybe in the next episode. Thanks for joining with me today, and see you soon. Goodbye.